a bit late. Let's start. Thank you. Okay, I'm going to be working on the order, so I think
you need to do so.
Okay, so filling space with knotted circles. I was inspired to give this talk so first of all let me say this is just an entertaining talk, this is not a research talk, but I will touch on some things at the end which are kind of quite exciting. And I was inspired to give this when I when a friend showed me this toy that she bought off the internet, and if I can just get rid of it, there we go. So you guys can pass this around, and she brought it over, and she said, "Wow, look at that! Fantastic device. If you put your hand in it, then it will go up and down your hand." Okay. And I looked at the shape, and I thought, "Wow, that looks like something I've seen in the books. It's called the Hopf fibration." And I'm still not exactly sure whether that is the Hopf fibration. At least it's not in the 19th sense. You have to modify it a little bit because that's one continuous string of metal. I'll come to that at the end. But I invite you to stare at that and try and figure out what's going on. Hopf fibration can be made from linking a whole bunch of circles together, similar to that picture. That's one circle, they actually have lots of them. And this, you can make it by taking a keyring, putting the other keyring into the first keyring, taking the third keyring and slotting both the first two keyrings into that, taking the fourth keyring and linking it with all the remaining keyrings, and so on. And you do that, and after about 100 times, or I think less, not about 20 times, we'll get to this beautiful picture. Just carry on and on. And eventually you can fill up all of space with these knotted circles. Okay. So, I want to describe it. So, I've decided what I'm going to do is I'm going to do the full calculation with you. Yes. And so if you get a bit lost in this calculation, don't worry, there'll be some nice pictures at the end. But let's get our hands dirty and let's try and figure out what's going on here. And maybe you can help me in case I make a mistake. Please stop me if there's something you don't understand. Okay. So we'll start with complex projective space. Now, those of you who went to Arnold Keats' talk will remember that this is the space of all lines through the origin in two-dimensional complex space. So I could say that's one-dimensional subspaces of two-dimensional complex space. Okay. So how are we to imagine that? Well, so there's the set of all subspaces. So yes, C2, there's C and there's another copy of C. This is C2. Let's call this axis the Z-axis and this the W axis. So each of these copies, remember this is a slightly misleading picture because each of these axes is itself a complex plane. Don't forget that. What is a line, or a subspace is just a line through the origin like that, L. And CP1 is the collection of all these lines. How are we to think about such a line? We can think about, we can write CP1 as the collection of things that looks like this. Maybe we can use homogeneous coordinates, where this notation is going to specify that line. And the notation is such that if I write that down, that is the same object as this object here. Where lambda is some scalar, which is not zero. That just says that to specify a line, it's enough to specify some point on the line up to a scalar multiple. Indeed. So each line is going to intersect this. So let's draw a circle here. Well, it looks like a circle, but is it really a circle? Well, what is this equation for the circle? It's going to be the modulus of z squared plus the modulus of w squared is equal to 1. So there's two components here, and there's two components here. So this is really living in 4 dimensions. So I can think of this as the 3-sphere. It's the 3-sphere in 4 dimensions. Good, so each line L is going to intersect that 3-sphere in a circle. Why? Because once I touch the 3-sphere, well, at this point it looks like I'm touching it at 2 different points, but remember that these axes are misleading. These 2 points are actually connected to each other. Because I can rotate this by the map which says z comma w goes to e to the I alpha z comma e to the I alpha w. And when you do that, and you rotate by pi, you'll get back here. Okay, and then you get to minus 1. So these 2 points are living in the same circle, and the circle is specified by this alpha. Now, and that point will still remain exactly, it will still intersect it still lies on the line, but there's a rotation action on the line which is going to keep it on the sphere.
I also think that as the line is actually a plane and it's having a sphere, that's also.
Yeah, the line is actually a plane which is cutting a sphere in a circle. So we can think about this, that circle as being the fiber of the map which is going to send z comma w to the homogeneous coordinates zw. Okay. So a point on this 3-sphere gets sent to the line which is intersecting it. And so in this way, for each point on the 3-sphere, we have a circle, namely the circle attached to the line which is intersecting the 3-sphere at that point. And so we've got a collection of circles, one circle for each point on the, for each point on the line we have a circle, namely the circle which keeps it on S3. And so for each line we have a circle. So this is called the Hopf fibration. So now from this one formula which looks completely silly, is going to follow all that nuttiness and beautiful pictures that I had on the board. Okay, I literally just replaced the open brackets by the square brackets and the comma by a colon. Okay, so let's go and work out what's going on. Okay, so what we need to think is we need to think of CP1, the collection of lines through the origin, as being isomorphic to the complex numbers union infinity. Right, how do we think about it like that? Well, if I've got a line in 2-dimensional complex space, I can basically just calculate its gradient. Here's my line, I can calculate W over Z. Okay, that parameterizes all the lines, except the line which goes straight up. So that's why I've added infinity here. And we also need to think of C union infinity as being isomorphic to the 2-sphere. How do we see that? Well, this is going to be stereographic projection. So let's work it out. So I want to see how the complex plane with the initial point is the same thing as the surface of a sphere. Let's draw the picture. This is now ordinary three-dimensional space. This is x, y, z. And then I draw a sphere of radius 1 centered at the origin. And then I project from the point at the top of the sphere, the North Pole. This way, I send out a ray of light. It intersects the sphere at a certain point, which I'm going to call A, B, C. And that ray of light comes down and intersects the plane at a point x, y. And in this way, as I shine this ray of light out in all the various directions, I will parameterize the entire plane by points on the sphere. The only point on the sphere which isn't going to be covered by this procedure is the North Pole itself. But that gets accounted for by the fact that it sort of maps to infinity. That's why I included infinity to the complex plane to get this nice and order. So let's work out the formula for this stereographic projection. What I want to do is I want to work out A, B, C in terms of x and y. Clearly they're determined by each other by this picture. So let's work it out. To do that, I'm going to need a formula for this line, a parametric equation for this line, and then I'm going to just see where the points on the line satisfy that a squared plus b squared plus c squared is what. When does the point on the line 2 squared? So what's the parametric equation for that line? Well, I've got to take 0, 0, 1, and I've got to take plus t times the vector pointing in the xy direction. Yes, that's right. So vector pointing in the xy direction is going to be x in the x direction, y in the y direction, and the z direction, I'm going down 1. So I'm just writing this vector out. So this is minus 1. Okay. So that parameterizes points along this line. But we want to find the point which lies on the 2 sphere. That means I'm going to need this, the x, y, and z coordinates must square to 1. So I'm going to need that t squared x squared. And the y coordinate is going to be t squared y squared. The z coordinate is going to be 1 plus 1 minus t. Right? Equals 1. I'm just trying to find for the value of t that's going to intersect the sphere. So let's solve for t here. Well, I get out if I collect terms in t squared, I'm going to get out t squared times x squared plus y squared, and I'm going to get out a plus 1 over here. The one that's going to come out here is going to cancel that one, don't have to worry about it. I'm going to get out a minus 2t, which I'm going to take to the other side. Then divide through by t. And this allows me to solve for t. So now to work out what a, b, and c is, I just got to plug in that t value into the equation of the line. So then I'm going to get out this formula. In fact, this is the formula that I want to use over here. So my point on the line is going to be x plus yi, which is living in complex space. This is this point there. And it's going to get mapped to, let's figure it out. I've just put in this value of t into the formula for the line. So the a coordinate is going to be 2x over x squared plus y squared plus 1. The y coordinate is going to be 2y over x squared plus y squared plus 1. The z coordinates, I'm going to put in this value of t. I'm getting 1 minus t, so 1 minus this, put it over a common denominator. It's going to be x squared plus y squared minus 1 on the top. Everyone happy? Good. Okay. so we've managed to see our CP1 is going to be identified on S2. So let's compose these. Let's stop this incredibly annoying phone. So we want to compose them. So first of all, I send it to that by that map, then I send this to that by this map. So I'm going to get an identification with S2 this way. And you work out what this does and you compose that together, you'll find that you're going to be sending ZW to modulus of Z squared minus the modulus of W squared, comma, 2Z bar W. Formula might look a bit strange. How is this supposed to be living on S2? Well, this is a real number, and this is two real numbers here. This is a complex number. So three real numbers lives in R3, and S2 is living in R3. Okay. So we've made that identification. Okay, now the interesting thing is, so just remind ourselves what we're trying to understand. We're trying to understand that map over there. So up to now, what we've discovered is that the Hopf map, I'll fix it up now. I want to think of my S3 as living inside C2, and then I'm going to map it. That's going to be my Hopf map H, and I'm going to map it to S2 by this formula. So I'm going to map Z, comma W, living inside C2. It's going to map to modulus of Z squared minus modulus of W squared. Now what we want, so we have a nice picture for that. Everyone can visualize the two-sphere. But we want to be able to picture this on the left-hand side, to be able to draw those pictures. To do that, I can use stereographic projection again. Because S3 can be thought of as living in R4 by a stereographic, or S3 can be identified with R3 union infinity by a stereographic projection in R4. Okay, all I have to do is just go and change this over here. So let me write that formula out over here.
So it should not be 2Z bar W.
Yeah, thanks. So S3 can also be identified with that by a stereographic projection. All I have to go and do is just take this formula, which I've worked out up there, and just adding z's everywhere. So the formula, let's write it out. So now, instead of thinking of this as the two-sphere, I'm going to think of this as a three-sphere. So originally this was the two-sphere. Now cross it out and think of it as a three-sphere. Originally this was the plane R2, and I cross that out, and I think of it as R3. And I'm going to use coordinates x, y, z to describe this point. This point over here is now going to be 0, 0, 0, 1 in R4. And this point here, where it's intersecting the three-sphere, I'm going to write that as z, comma w. This is the two real components and two imaginary components. It's going to count for that. Okay, so the same formula as before is going to identify S3 with R3 union infinity. Let's write it out. there. I made a mistake here. This is the wrong way around, right? This guy should be left. So in the R3 it's x, y, z. We won't worry about the point at infinity, and that's going to get mapped to that same formula. So it's 2x over x squared plus y squared plus 1. Plus now is z squared. 2y over x squared plus y squared plus z squared plus 1. Comma 2z over x squared plus y squared plus z squared plus 1. And the last one is x squared plus y squared plus z squared plus 1 minus 1 over x squared plus y squared plus z squared plus 1. And I guess I should have just taken that all out as a common factor. Right, so that's the way we're going to draw our pictures, because we've got this identification of S3 with R3 in that way. Here's a beautiful fact. And this fact is something that physicists understand, but mathematicians seldom use these coordinates. Is that we also use phase coordinates to describe S3. Okay. What do I mean by that? So I've got my point living in S3. Z, remember it consists of a pair of points Z and W. And I'm going to write it like this. Cos theta over 2 times e to the I phi 1. Right? It's just a complex number, so I can write it in this form. I'll explain now why I can write that as cos theta. And I can write W in polar form as sin theta over 2 e to the I phi 2. How can I describe it like this? Well, because clearly then I'm going to make sure that z squared plus w squared equals 1. Cos squared plus sin squared is 1. So that's a very clever parameterization of S3. Everyone happy? I want to find two complex numbers such that the sum of their modulus squares equals 1. This is a clever way to write them. Okay, good. We'll get to that. Yeah. I could use any angle there. So now we write this, cleverly realizing that there's a phase coming into play there, but what's really important is the global phase and the difference in phases. So I'm going to rewrite it like this. I'm not going to worry about this modulus in front, but the phase factor, I'm going to write it as e to the minus I phi over 2. I'm going to find a new symbol here, phi, with the difference phi 2 minus phi 1. And then I'm going to write e to the I phi 1 plus phi 2 over 2. Let's check if this works. Well, I'm going to get out a minus phi 2 over there, which is going to cancel the plus phi 2, and I'm going to get out phi 1 over there. So it's just a simple rewriting of it. But it's good to separate it like this, because now I see how the phase is transformed. So this guy is going to have a plus I phi in front of him. And he's still going to have this global phase. Let's see if that works. I'm going to be plussing the I, so I'm going to be subtracting off the phi 1. I'm going to kill that phi 1. And I'm going to be doubling these, so I'm going to get out the phi 2, which is what I need. Okay, if we want, let's call that coordinate phi 2 plus phi 1. Let's call that psi. So now what I've really done is I've rewritten the whole thing as e to the I psi over 2. And this is written as e to the I psi over 2. Okay, so to describe a point in S3, suffices to give me three angles, theta, phi, and psi. That's a nice new parameterization. Obviously it breaks down at some point, because this would imply, each of these is a circle, so this would seem to imply that the S3 is a circle across a circle across a circle, which isn't true. But it's the same way as ordinary stereographic coordinates on a two-sphere also breaks down to pulse. Okay. So if I describe the Hopf map, which is over here, where's our Hopf map? Okay, so
It's up there. Half of it is also.
Yeah. Sending Z over W, filling in. Okay. Take it slowly. Got a map from S3 to S2. That's the Hopf map. It's sending Z over W into Z squared minus W squared modulus 2Z bar W. And we're trying to understand this map. Okay, so if you've lost me up to now, this is what's going on. But some map, here's the explicit description of it. I'm trying to understand how it works. So what I've done is I found another way to describe points in S3 by these three angles. Okay? If I think of the points in S3 by these three angles, theta, phi, psi, look what happens. I've got to calculate modulus of Z squared minus modulus of W squared. It's going to be cos squared theta over 2 minus sin squared theta over 2, giving me, first years all that.
Wow.
Cos theta. This guy, but Z bar W. Z bar W, I'm going to get out from the cos theta over 2 times sin theta over 2. Sorry, there's a 2 there. And the phi's are going to be killed with the Z bar making it into a plus, which is going to, the psi's are going to be killed. So I'm going to get double up on the phi's. So I get sin theta over 2, cos theta over 2 times e to the r phi. Times 2. And the sin theta over 2, cos theta over 2 times 2 gives me? Sin. Good. So I'm getting out sin theta e to the I phi. And that's the reason why I was halving those thetas, because now I can really think of this as being points. What is this point in R3? Or this is a point on the two-sphere, and it's literally the point on the two-sphere, which is given by I've forgotten the name of these spherical coordinates. Sorry?
As the blue coordinates something else.
No, but what are these coordinates called? Just spherical coordinates. Really?
Yeah.
Spherical coordinates, good. So there's my theta, and this angle here, which I projected down, that's my phi. Okay, there's x, y, z. So in this parameterization, it's very nice, because we see that the fibers of the Hopf fibration, it simply forgets about the psi. See, there's no psi over here. So the global phase is getting ignored.
Yeah, but your Z and your W are essentially being multiplied by the same factor, right? On the right. So I mean, they should be the same. They're both being multiplied by e to the psi over 2, the I psi over 2.
Yes.
And so you can forget it because
Yes.
you're multiplying by the same factor.
Yes. Indeed. Okay. Okay. Let me just remind myself where I am. So we've calculated new coordinates, we've got a nice way to understand the Hopf vibration, at least in these new coordinates, but we still need to work a little bit more to understand what the fibers of this is going to be in R3. So to do that, we make two observations. First observation, the crucial one, and I guess I'm not going to get to my slides, I'm too bad about that. Let me just check. What's the time now?
Of course.
The first observation, so what I'm trying to understand is what happens over here when I rotate in S3, what happens when I rotate by this S1. Remember that I've got this line and it's intersecting S3 in a circle. I'm trying to understand what happens on that circle. Those points on that circle are where I set ZW to e to the I alpha times Z, e to the I alpha times W. So if I look at the way I've written it over here, obviously, well, it's obviously not that obvious since I have to look at my page again. But, yes, let me write this down. Along that circle, the modulus of Z is obviously preserved because the modulus of W is also preserved, but I'm just going to focus on one of these. Modulus of Z is obviously preserved, I'm just multiplying by phase factor. What's the modulus of Z squared? If I look up in those coordinates, it's cos squared theta over 2. Okay, it's just a sort of a trivial observation, but it has an important consequence. Let's work out what this means in spherical coordinates. Okay, so this is staying constant. The modulus of Z squared done. I'm thinking very badly. Okay, let me write it up and then maybe you can help me. I want to think of S3. Okay, so in terms of the formula for stereographic projection, this square is staying constant. And the modulus of Z, this guy here is what my Z is, and these two guys here are what my W is. So I'm saying that the modulus of Z equals squared equals that. Meaning that the modulus of Z constructed over here squared equals that. So we write out that equation. Let's write it out. So I don't have to worry about, well, yes, I'm going to need to worry about it on the bottom. So I'm going to get out x squared plus y squared times 4. I'm just writing out that modulus of Z squared. This is the real part of Z, that's the imaginary part of Z. Now I've got to square the thing on the bottom as well. This is when things get exciting. And this is going to be equal to cos squared theta over 2. Okay. So what's going on here is I'm saying I'm at a certain point on the two-sphere parameter, I'm at a certain angle from the pole theta, and the fibers of the Hopf vibration are the points where I just sent Z goes to e to the I alpha Z. So when I said Z goes to either I alpha Z and same for W, this certain equation is preserved, the modulus of Z squared is preserved. What that boils down to means that the fiber of the Hopf map at this point here, thought of as living in R3, must satisfy this equation. Okay. So let me write it down here. So I'm thinking of this as being S3 and being mapped over by the Hopf map. Okay, so what does this mean? Let's analyze this equation. This is an equation XYZ R3, so it's going to be a surface. One equation R3 traces out a surface. But let's look at it a little bit more. We see that x squared plus y squared or x and y only feature through the combination x squared plus y squared. So, in other words, as if this is x, y, and z here, as I rotate x and y, if a point lie on the surface over here, when I rotate it, it will still lie on the surface because it's only featuring to x squared plus y squared. So this is the surface of revolution. Okay, just from the way that x and y feature in the equation. So all I need to do to feature the surface is I just need to draw it in one plane and then rotate that. So I'll draw it in the xz plane. I'm going to draw this surface. So secretly, I'll tell you the answer. The surface is going to be a torus in R3, a donut. And I'm going to just take a section of it in the xz plane. To get the rest of it, I just need to rotate around the z plane. Or around the z-axis. So in the xz plane, I just put y equal to 0, and I'm going to get out x squared over x squared plus z squared plus y squared equals that. I can then take square roots of both sides. So I've got 2x over x squared plus z squared plus 1 equals cos of theta over 2. This is an equation for a curve inside the xz plane. And if I just rearrange this formula, you'll see that I'm going to get out x minus sec theta over 2 squared plus z squared is equal to tan squared theta over 2. It's multiplied through and complete the square. So in the xz plane, we're getting this picture. We have a circle over here, and yes, we also get a circle over here because I took that square root just now. Square root as the consequence of me only focusing on the one circle, but there's the other circle as well. The center of the circle is at sec, that distance is sec theta over 2. And the radius of the circle is tan theta over 2. So the fibers, so what I've learned, let me summarize what we've learned that if you had a certain angle from the North Pole at an angle of theta, and you consider all the points that have that angle of theta, so that, and then you look at what maps to that curve under the Hopf map H. We'll see we trace out the torus, and the distance of the torus from the z-axis is sec theta over 2, and the radius of the circle in the torus is tan theta over 2. Who's happy? Who's not? This is a sort of fundamental. I'm losing a little bit, eh? Okay. No. Okay. Okay, so we're trying to understand the fibers of the Hopf vibration. We saw that the Hopf vibration sends this torus to that point. What happens when I move this, when I increase the value of theta? Say I were to increase it to over here. Say that would be my new theta going down there. So as I move down the two-sphere, down the lines of latitude, what would be the inverse image of that? Well, again, it's going to be a torus. But now, since I've increased theta, the radius of my torus is going to be a bit bigger, and the distance of my torus from the z-axis, or that center point, is going to be a bit bigger. So I've got another torus, which captures this torus. And this is where it's obviously going to get difficult to draw. So I'm just going to go like this. And the white torus is inside the green torus. Okay. So as I go even down, eventually these toruses are going to get bigger and bigger. And I'm going to, by the time I get to over here, this torus is just going to be a normal sized torus. When I get right down to the south pole, theta over 2 is going to be pi over 4, and so, pi over 2, so the radius of the torus goes to infinity, and so at that point, when I'm at the north or the south pole, the inverse image of the south pole is going to be the entire z-axis. What's the inverse image of the north pole? Well, I'm just going to look what happens to this equation when I'm at theta equals 0. Then I'm going to get out x minus 1 squared plus z squared equals 0. And this is just a torus that's been degenerated to a circle.
So when it's initially inside of this provided?
Yes. Yes. Yeah.
Oh, it's
sorry, it's in the x.
You just got to say that tan. The tan is 0. So the thickness of the torus is 0, but its inner radius is still 1. Yeah. The sec of 0 is 1. So you get a horizontal circle.
Radius.
So I guess I get a circle over here.
Yeah.
So thanks.
It's inside all.
It's inside all the toruses.
Yeah, yeah.
Okay.
So inside the one on that side.
Yeah. Okay. Luckily, that's why I have the slides. Okay. It's inside all the toruses get squashed out like that. Okay. I haven't quite completed the picture because I've understood the fibers very nicely. But what I'd really like to do, what I've understood now is I've understood the fibers of a line of latitude. But I want to understand the fiber with just a big point. To do that, I make one more trivial observation. So my first observation was that. And my second observation is going to be, if I just look at these coordinates, ZW, I saw an obvious relation that I can write down. If I multiply this by sine theta over 2, then I'm going to get similar to this. So let's write that down. So if I take Z, I multiply it by sine theta over 2. I want to get that. I'm going to get something times W. So if I multiply Z by sine theta over 2, then I'm going to have to multiply W by cos theta over 2. Are these two things equal? Almost equal. They're both got a sine theta over 2, cos theta over 2. But this guy's sitting with a heat of minus I phi over 2, so I'm going to have to give him another e I phi to catch up. So I've got this sort of obvious relation between Z and W. Let's write out what that means in real imaginary components. So, well, let me write this way. So I'm going to take W to the other side. So W is going to be equal to tan theta over 2 times e to the I pi z. So this is a relation between W and Z. They're two complex numbers. Let's write out the real components.
Theta over 2, tan of theta.
Okay. Real component of this equation is saying that W1 is going to be tan theta over 2, and then, well, if I rotate Z by phi, I'm going to get out cos phi times Z1, and minus sine phi times Z2. Okay? Let's try and understand what this means in terms of stereographic projection. So this is an equation between W1, Z1, and Z2. So this is W1, that's Z1, that's 2, that's Z2. I could just replace those appearances there by these expressions. Then the equation is not going to worry about the denominators. And in the top I've just got these linear numbers here. So I can just drop all the 2's and I can just replace these W1 by Z. I can replace Z1 by X and Z2 by Y. So this is what that equation or that observation boils down to in R3. What is this in R3? This is the surface of a plane. Okay? And clearly the way the plane works, so it's a normal vector, theta over 2 and phi. Right, so what I've done here is I take a plane and I intersect with the torus. So I just grab one more color, and that would be wonderful. I'm trying to understand the inverse image of this particular point. And we can say that point over there. Because this point has got a theta value and a phi value. So maybe I should tidy up my picture here. So let's see, this point has got a theta value, which maps down over there. So I can think of that point as being that thing over there, project it onto the plane, and then I get this thing here, and it's got phi value. Trying to understand the inverse image of the yellow point under the Hopf map. And from this observation, I've realized that it's going to point at theta phi, the inverse images lie on this plane. So all I'm going to draw, so first of all let me draw the inverse image of that line of latitude. It's going to be a torus with, we can even tell you exactly where the dimensions of the torus are. And that point is going to correspond to, well, it's certainly something that lives on the fiber of that point would have to live on this plane. So I calculate the distance pi here, and then I take a plane through the origin whose normal is parameterized by that angle. Okay, so I take a plane and I slice the torus through the origin with that plane, and where it slices the torus, that's going to be the inverse image of that yellow dot. Okay, and oh, I knew this chalk would bite me one day. Okay, let's make it a red dot. And that circle is the inverse, is the fiber of that dot. I take a plane, I slice the torus. And why will I get out of circle? Well, I could prove it from these equations here that I'm going to get out of circle. But that's a rather remarkable point. I'm claiming that there's a way you can slice a torus with a plane in such a way that the cross-section gives you a circle. And how much time do I have? 5 minutes. Okay, let me show you the pictures of that thing. While we wait for it to warm up, let's remind ourselves where we are. Okay, so we started when following up, we saw that to every line in C2, it intersects the sphere S3 in a circle. So that means to every line in S2, in C2, I can associate a circle. For every line I get a circle, different lines get different circles, so I get a whole bunch of circles. This is the Hopf fibration. And I could think of that circle as being the fiber of this map. Over there. It's the fiber of this map. The only freedom I've got left is to rotate this by an angle. And, well, that is the formula for the Hopf fibration. I simply just took away brackets and replaced them by square brackets. Then I worked out what this means. I figured out that CP1 was ultimately isomorphic to S2 on the left-hand side, so that was what's on the right-hand side. I could think of this guy as living on S2. On the left-hand side, this guy was originally living on S3, living inside C2. By stereographic projection, I can think of that as living in R3 union infinity, and by a bunch of algebraic manipulations, I rewrote my Hopf map as the map from S3 to S2, given by this formula. Then, by parameterizing S3 by these special angles, very clever parameterization of points in S3, I figured out, I could figure out the fibers of the Hopf map. I saw that lines of latitude map backwards into toruses, and a single point is the intersection of the torus with the plane. Let's see if we can get some nice pictures of that. Okay, this is summarizing what I'm saying. Yeah. Okay, this is summarizing what I'm saying, except it's got a little extra tweak there. So, there's the line of latitude, and there's the inverse image, is the torus, and the torus is being sliced by a plane, and that plane's going to, so that's the inverse image of that light blue circle, is the inverse image of that light blue point. And its plane is going to intersect the torus. And as these planes rotate, they intersect the toruses in different circles. So let me give you that picture here. So this is the inverse image of one of the points, and it's a plane passing through the origin in that direction. Yes. Don't worry, ignore the blue line. The blue line is from the other side. Now I rotate my phi, so I change my phi. That means that my plane is going to rotate around the z-axis. Okay? And it's going to intersect the torus differently. It's going to rotate like that. So we get this kind of picture. That's what happens when you change phi.
There should be another circle too.
As far as I'm only worrying about the one circle, but this diagram nicely illustrates that if I consider 2 points, that point and that point, for example, then both of them would be the plane intersecting the torus. So both of them are going to trace out these circles. And if you think about it, that means that those 2 circles are going to be knotted, because if you slice the torus like this and slice it like that, those 2 circles get knotted, because this one's coming inside that one. Okay, and there you can see how those circles are knotted. Let me just show the picture again. Otherwise, it's a beautiful physics article in Nature 2008 where they demonstrate how certain electromagnetic fields. There's a solution to Maxwell's equations, which is the Hopf fibration. Very beautiful. There's a nice picture of the same thing. You see how this is the one slice of the torus, and then all I've got to do is just rotate around the z-axis to get all the other circles. That's, if you didn't like the modern stuff, that's Penrose's picture of the same thing, which is perhaps a little bit more artistic. And indeed, you can see how these toruses fill out space. And each line here is the intersection of the torus with the plane. So there's a torus, there's a bigger torus, an even bigger torus, and they're approaching the z-axis. What I haven't had time to do is to explain the connection with homotopy theory and to explain why the Hopf map can't be homotoped to, or is not homotopic, and essentially that boils down to the fact that these fibers are linked, which means that I can't unlink the fibers, which means I've got a non-trivial map from S3 to S2, which is what got Hopf all excited, because it wasn't known at that point. It wasn't known if you could wrap the 3-sphere around the 2-sphere in a non-trivial way. It couldn't be deformed away. Okay, so I'm going to ignore that. There's a whole long story there about the homotopy groups of spheres. You might then wonder how the spheres can map to each other. You get these incredible tables. So this Hopf fibration sort of starts off people wondering, okay, so there's this weird map from S3 to S2. What about mapping S4 to S2, S5 to S2, S6 to S2? And you get out these kind of things. For example, we see that this is the collection of different maps from S3 to S2. So pi I map is mapping from S3 and n is equal to S2. So when I equals 3 and n equals 2, we've got a z there, which is telling us that there's z many ways to map a 3-sphere onto a 2-sphere, and that's generated by the Hopf vibration. It's just multiples of the Hopf vibration. And if I go over here, you see that there's Z2 cross Z2 ways of mapping the 3-sphere onto the 2, of mapping the 12, of mapping the 12-sphere onto the 2-sphere. And it gets more and more complicated as you proceed to the right. And this is an incredibly complicated table. People then study stable homotopy theory, which slightly simplifies this. Let me just finish off the talk by mentioning 4 cool things where the Hopf vibration also shows up. The Hopf vibration also shows up if you stand against the wall, and I invite you to do this. Put your arm straight so that you just touch the wall. Then keep your hand straight, always trying to endeavor to keep it straight as I rotate round. And then come back, and my hand got shorter. You won't believe me, but it's true. Go and test it for yourself. Now I'm going to do it again. I can touch the wall again. And this has got to do with the fact that this is essentially the Hopf vibration, but in a different language. Beautiful fact. This stuff, by the way, I'm not from the mathematical intelligentsia. This is a Hungarian, Julius Kovacs, demonstrating this technique. It also shows up as a crucial ingredient in the beautiful periodic solution of the 3-body problem, which was discovered in 2000. These 3 bodies that acting on gravity, they chase each other around a figure of 8. And it wasn't known that there could be such a weird solution, but it is. And the way the Hopf vibration shows up here is that, well, I've got 3 bodies in a plane. The moment of inertia is conserved. The moment of inertia says that they must be living on S3. And then since I've got rotational invariance, that's going to give me a map from such a collection onto S2, and that turns out to be the Hopf map. So it shows up in this beautiful solution. It also shows up in quantum mechanics because you have invariance under phase, and it also shows up in the modular flow in space of lattices. But its relative shows up. Leon might recognize this picture because this is from the Knots of Dynamics talk at ICM 2006. If you're interested in number theory, then the analog of the Hopf vibration is the modular flow in space of lattices in the plane. And now the inverse image, the analog of the North Pole, is going to be the degenerate lattices. The degenerate lattices satisfy the equation coming from Einstein's series, which turns out to trace out a tripfold knot. And when you change the lattices by a modular transformation, they wind around this triple knot in incredibly beautiful ways. Okay, this has got links with, this is essentially a whole bunch of number theory hidden in here. Okay, so we've got these 4 beautiful pictures, and all coming from that keyring. By the way, this is a beautiful website to visit. Etienne Gies and his collaborator Just Lees, who made this picture, have released a beautiful set of videos on the internet, www increasing the amount of reward. Okay, so we've done so long, so I think we can just have tea and everyone can just go.